Welcome back to another chemistry video. Today we are learning about something called Dalton's law. This is Mr. John Dalton. It's the same guy who had Dalton's atomic theory, if you remember that. So this is Dalton's law of partial pressures. Perhaps you feel like you have a lot of pressure in your life right now. So this is dealing with not quite that kind of pressure, but Dalton's law of partial pressures, not total pressure. This actually is like the simplest gas law that there is. Gonna warn you, sometimes the application of this one can get a little rough, but the actual original idea is very simple, which is kind of nice. Okay, what did he say? Well, try to give you a scenario first. Let's say you have some kind of container that's gonna hold a gas. So I've got maybe this box, this container. Let's pretend this is like a steel container. We can't change the volume. And we're gonna fill this container with a gas. Okay, maybe there's like a lid up top or something, whatever. So we're gonna put some gas in here, and we end up putting a mixture in here. So I'll use some different colors. Let's say first you put in a little bit of helium and not very much helium. Let's say helium is this pink one here, and you put in that much helium. Now, remember these are gas particles. Gases move very quickly, so they'd all be kind of, you can draw the whoosh marks if you want, moving random different directions like that. And as they move around, they bounce and they hit into the walls of the container. So bang, they'd kind of imagine them all like ping-ponging around, right? As these little particles hit into the walls of their container, they exert a pressure. Let's say that helium had a pressure of, I don't know, 0.25 atm, okay, quarter of an atmosphere. This gas, when you put it in, it's going to take the shape of its container, right? That's one of the basic properties of a gas. It's gonna spread out all inside this container until it totally fills the container up. Now, it's not a lot of gas. It's only a quarter of an atmosphere, so a quarter of the pressure that you're experiencing right now, or roughly. That's not a whole lot, but it spreads out, it fills the container. What if we put another gas in there? So I'm gonna get a green pen. Let's say we put some hydrogen in there, okay? And I'll draw hydrogen as the little doubles because it's a little diatomic molecule. So this green one, this is hydrogen. And maybe I put a little more hydrogen in here. Okay, and I'm not going to draw all the whoosh marks, but that is also bonging and binging around. And let's say that this hydrogen is equal to 0.5 atm. Okay, this hydrogen also, when you put it in, the green one, it honestly just ignores the helium. It pretends like it's not there. It's also going to spread out, it's going to fill the container, and it's going to start exerting a pressure on that container because of every time it hits into the walls, it creates a little force, a little force, a little force, a little force, and that adds up to the pressure. So these gases basically ignore each other. They will bump into each other and bounce off a little bit, but it doesn't seem to have that great of effect on the overall pressure. So right now, take a wild guess, guys. What if you wanted the total pressure inside of this container? Pink is 0.25 and green is 0.5. What do you think the total pressure is? Yeah, the total pressure inside that container right now is 0.75. You literally just add up the partial pressures. That is what Dalton's law is. If you were to add a third gas, so I don't know what gas you want to put in here. Let's say fluorine, put a nasty. We'll put in fluorine gas, we'll make it a nasty yellow color, okay, because fluorine's pretty nasty. Let's say we put in a little bit of a fluorine gas in here. Not really to scale, okay, guys? There's your fluorine gas. And maybe that's another 0.25 atm. If you add that all up, what do you get right now? Yeah, you should be saying 1, okay? 0.25 plus 5 plus 0.25, you get a total of 1 atmosphere. So in there would be equal to atmospheric pressure right now. That's a simple example, but that is Dalton's law. If you put that into more formal terminology here, you get P total that means total pressure, is equal to P1 plus P2 plus P3, etc., ... These would be your partial pressures. In this case, we had 3, so it would be pressure of helium plus the pressure of hydrogen plus the pressure of fluorine is equal to the total pressure. That's literally what I just did right there. That's all His law is, guys. It just says they add up. They add together. There are some important applications. Yes, that's really simple. It is really simple, but there are some really important applications. I hope you know that our air, what's you're breathing right now, is very similar to this. It is not one thing. Think for a second. You tell me, what is in the air that we're breathing in right now? You should be able to list multiple things if you remember biology or earth science or any of those classes. What's in the air? Well, hope you said oxygen, right? We'd be dead without oxygen. And maybe you said carbon dioxide and nitrogen. Those are all in our air. Actually, the biggest part of our air is nitrogen. So we have nitrogen, we have oxygen, we have carbon dioxide, water vapor. There's actually a little bit of argon in there, and there's a few other trace gases as well. Those are probably the more important ones. And so our air is a mixture of all of these added together, and our total pressure is a mixture of all of these. Roughly, I think it's 71% nitrogen and like, this might be off. I'm very sorry if this is wrong. Like 21% oxygen. Carbon dioxide is really not much. It's kind of like a 1%-ish. That's like a 1%-ish. That's like less than 1%-ish. This one can vary. So mostly nitrogen, and then the second highest would be oxygen, and then carbon dioxide, and then it gets smaller after that. And that makes up the air that we breathe. Okay, a couple of important application points from this. If gases do this, if you can put multiple different gases in this container and they all spread out, they basically ignore each other and the pressures add up. So in other words, like why would they not add up? Okay, if you're cooking, I was just baking something earlier tonight. Let's say, you know, there's one of those little like glass Pyrex containers, right? And you put in some flour. So we have some flour down here. Maybe you put in a half cup of flour. And then you put in a half cup of water. Do you know this? You've been in the kitchen very long. Is a half cup of water and a half cup of flour, does that equal 1 cup? Not necessarily. They actually kind of can smush together a little bit. And I would say, I don't know the exact number there. You can go in your kitchen and try it out later if you want to. But that's going to be less than a cup. They actually interact with each other. The water absorbs the flour, and it would actually be less than a cup. But that's not true with these gases. When you add them together, they just straight add. So what's an application of that? Well, it does mean that the size of gas particles, it says this way, is negligible, sorry if that's spelled wrong. The size of the gas particles is negligible. Negligible means not important or it doesn't matter. They're so small, the gases are so small that the size doesn't matter. This is not to scale at all, okay guys? These are little teeny tiny little gas particles in a relatively big space. And so it doesn't matter if it's helium or hydrogen or fluorine. These are all different size gases. Even if we put a big gas in there, like, I don't know, a carbon dioxide, that's a relatively large-ish kind of gas. It doesn't matter what size the particles are. They all kind of behave the same. Therefore, the size of the particle and actually the type of particle, as long as it's a gas, does not matter. It only matters how much. As far as determining pressure. If you add more dots, more gas, then you get higher pressure. But the type of gas really does not matter. That's going to come in, more into play in tomorrow's lesson, okay? But it's an interesting application of this one. All right, how would we use this? Let's say we got this right here. Okay, calculate the total pressure in ATM inside a 5-liter container with 1 mole of nitrogen, 0.5 moles of oxygen, and 0.25 moles of argon. Assume a temperature of 20 degrees and a rigid container. What does rigid container mean? Rigid means like hard and it's not gonna move. It's not squishy, it's not like a balloon. So the volume will not change, okay? That's what that means. So rigid container, you wanna find the total pressure inside that container. We're given different numbers, and your first inkling should be just to add those numbers together, and you would be correct to do so, but here's the deal, guys, that's in moles. So you have moles, moles, moles. If you add those together, so you have a part nitrogen, part oxygen, part argon, when you add them together, you're gonna get the total. That was Dalton's law. The deal is that's gonna be the total in moles. We want the total in pressure. Do you see a way that we can get pressure here, guys? It actually goes back to the last lesson. The ideal gas law. So do you see a way that we could answer this and actually get pressure? Well, here's what I'm thinking. I would add these up, get my total moles. Okay, moles will add together as well, and so you can kind of use that as a bit of a stand-in. So I'm gonna do that. So I've got 1 mole nitrogen and 0.5 oxygen and 0.25 argon. Okay, I don't need that 0. Add that all together, 152, so you get 1.75 moles total. So I know my moles. What else do I know? Look at your other numbers. Above this one, what's this? Yeah, liters is a unit of volume. So I have volume, I have moles, moles is N, and I have temperature. What can I do, guys? I got V, T, N. Is that ringing a bell? I want P. Yeah, you can use the ideal gas law. So I'm gonna plug this into PV equals nRT, and I'm gonna solve for that pressure. That's what I'm solving for. By the way, if you wanted to, you could take each of these individual numbers and solve them individually, PV equals nRT, and get pressure, and then add up the pressures. I just think it's easier to add moles because like moles literally add, it's a number. They add together. And so I'm gonna go ahead and get total moles and then calculate pressure from that. But you could do it the other way if you wanted to. I just think it's a little bit more work. Okay, let's plug and chug. V, so P is what I'm solving for. V is 5 liters. N, that's what I solved for here, 1.75 moles. R is our universal gas constant. That would be, very good, 0.0821 liters atmospheres over moles Kelvin. It's always a big one. And temperature in Celsius, can't be used in Celsius. What do I need to do? You need to convert to Kelvin. So you would take 20 plus 273. Go ahead and pause now. I want you to solve that for pressure. Alrighty, and this is a tricky one. We actually, because of this number here and because of this number here, we only are allowed 2 sig figs. So with 2 sig figs, we get a pressure of 8.4. Pressure will be in ATM because of the R factor and the units for R. So that's 8.4 ATM. That is what they asked me for. So good to go. Very nice. There are a couple other applications of Dalton's law. One of them is a little thing called collecting a gas over water. And this is kind of just a small point here. Collecting a gas over water. That might sound a little funny. It kind of is a little funny. This is a lab technique, all right? And I've seen this done When I helped out with UOG here on island and saw some of their labs, they did this in their labs. It's still used today. It was more so used kind of in earlier days of chemistry, but it's still a valid method. So it's a way to get a gas, because gases are difficult, right? Because like air is a gas. And so if you're trying to collect, say, just oxygen, you don't want to let that mix with air, because then it's not gonna be pure anymore. So one way to get a gas and try to keep it pure is this way. What do? Okay, you'll have some kind of reaction. So let's say I have a test tube here, and there's some reaction inside this test tube, okay? And I'm gonna draw some bubbles. It's whatever this thing is down here, it's producing a gas. All right, and so you'll fit maybe a stopper to the top of it, and you'll put a tube, like a little plastic tube kind of deal in here. And I'm not the best artist, I'm sorry. And that tube you're gonna squish into a beaker. I kind of drew this wrong, so my beaker's gonna be really fat, all right? Sorry. Here's my big fat beaker. So you're gonna put this down into a beaker, yay. And then you're gonna put another container basically on top of it. So maybe, I don't know, we'll just draw an Erlenmeyer here because of the space I've got. So you put some other kind of container on top like this. And that's not, just pretend it's a perfect drawing, all right? Beautiful drawing. And what you'll do before you start this reaction is you'll fill this container, this beaker, with water. And actually, initially, this is filled with water. So this container, I'll draw you before and after, okay? It starts out all the way full of water. But this tube, you're making a gas in here. It's bubbling. As it bubbles, it pushes the gas up the tube. It's got nowhere else to go. Up the tube's gonna come down, and then it's gonna bubble up in here like this. So you're gonna start making bubbles in here. As they bubble up, the air goes up, right? It's lighter than water, less dense than water. And so it's gonna bubble up, and eventually there's gonna be air in here, or gas in there, and it's gonna start pushing that water down, and the water will just kind of escape out the bottom. So it starts out 100% water, and then as time goes along, all of a sudden you'll see an air bubble starting to form as it bubbles up like that, and then that air bubble will grow. This is kind of fun to do. Actually, I did one lab for you where I did this. I did it in a test tube, but they were like, we bubbled something up into a test tube and then we collected it. And eventually you'll have almost all gas. And actually, if you let it go long enough, you will have 100% of your gas in here. Okay, and then you can real quick put a stopper on the bottom once it's completed. And then you flip it over and yay, you have whatever gas you're trying to find. So that's kind of a cool method. Here's the problem with it. As it bubbles, the bubbles have to pass through water first, because that was full of water initially. And then as the gas comes in, the water comes out the bottom like that. And so it has to go through water. As it does that, some of that water will inevitably turn into a gas itself, right? Because water has something called water vapor. Like, in other words, it starts to evaporate. So in this solution here, let's say we are trying to get oxygen gas, or maybe even ammonia. Okay, let's say we want ammonia. So this is producing ammonia gas. That's what's bubbling up and through the tube. When you're done and you have a tube of gas, it will be mostly ammonia, that gas that you're trying to make, but it will also be some water vapor, H2O gas, because some of it evaporated as you were collecting it. You say, well, what's the point of this if it's not pure? Like, I still didn't get a pure gas. Well, the water doesn't usually affect whatever experiment you're gonna do with the gas, so it's usually not a big deal. And also, we have this nice thing called Google. Used to be big published books in chemical laboratories, and it can tell you the standard vapor pressure, okay? So you can see something, maybe in some problems, called vapor pressure of water. And this is standard. Water will always evaporate so much at a given temperature, okay? And maybe, I don't know, maybe it's like 12.5. It's usually an mmHg at 25 degrees Celsius. I made that up, I don't know what the number is. But they'll give you a number. The vapor pressure of water at 25 degrees Celsius, 12.5. When you see that vapor pressure of water or you see collected a gas over water. If you see either one of those, that is a red flag. Okay, that's how I think about it. Should be like a little bell or alarm ringing in your head, like, hey, ding, 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 wait a minute. It's collecting a gas over water. We have a vapor pressure of water given to you. That means it's not a pure gas. You need to subtract the vapor pressure of water, and they're gonna give you that number, so don't worry about it, okay? Subtract it out before you start solving the problem. And that way you're just looking at the pure gas and you're not looking at the water. I'm gonna say that again. So when you collect a gas over water, you see that phrase, or you see a vapor pressure of water given to you, which they will give it to you. I will give it to you. You need to subtract that water from your original pressure. Subtract the pressure water from the original pressure you got to get just the pressure of that gas you're looking for. Otherwise, you're including water and it's gonna mess up your calculations. Okay, let's work an example. It might make more sense if we work an example. For instance, this one. Okay, calculate the number of moles of a gas collected over water. There's your red flag, ding, 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 ding. You need to subtract the vapor pressure at 30 degrees. The container is 0.5 liters with a total pressure of 820 mmHg. See, they gave it to you. The vapor pressure of water at 30 degrees is 31.8 mmHg. When you see that, the very first thing you're gonna do is subtract out the vapor pressure of water. This pressure is total pressure. It includes water and it includes whatever gas I'm looking for. We don't want that, we just want the gas, so we're gonna subtract it, okay? So really simply, you take that 820 mmHg and you subtract the 31.8 mmHg first, and then we'll continue on. All right, go ahead and put that in, or maybe some of you can do it in your head. We are subtracting, so we can only keep the least number of decimals. My calculator answer is 788.2. I'm only allowed to keep 788. I don't know what gas this is. Let's say this is oxygen. I don't know. Whatever it is, okay? There's 788 and then of just that gas and not of the water. Okay, to finish solving this one, what are we looking for? Calculate the number of moles. So I'm trying to find N, that's my question mark. At 30 degrees, that is your temperature. 0.500 liters, that is my volume. And pressure is this here, and we just calculated it. This is my pressure. Now don't forget, you are gonna need to convert here, okay? Pressure wants to be in ATM, they gave you mmHg, so you want to divide by 760 to get rid of that. I've got a T, a V, a P, I'm solving for N. That sounds like ideal gas law to me, so we're going to plug and chug into PV equals nRT. Don't forget to convert this first, so you go 788 times, there's 760 millimeters of mercury in 1 ATM. So basically divide by 760, and that gives you ATM. That's what you put in there for pressure. Okay, pressure must be an ATM. I'm gonna leave that up for you guys. You go ahead and solve that on your own time. Or you can pause now and solve and compare answers. All right, I do want to work one more example with you. We're going to go back to the overall Dalton's law. So remember, the idea is you can add up the pieces and that adds up to the total pressure, okay? And I'm not going to lie, this is a bit of a monster. We haven't had a monster problem in a while. Consider the following apparatus. That means this, you know, it's an amazing drawing, right? Containing helium in both sides, so both sides here, at 45 degrees Celsius. Initially, the valve is closed. This is the valve. That's like, you can like spin that little thing and basically it opens and closes. So these would be two like glass containers that they linked together, and you put a stopcock in the middle and you can open or close that. Okay, so it's closed, the valve is closed. Calculate the pressure of the helium gas after the valve is opened. Maybe colors will help here. Let's make this guy green. So let's say this side is green. I got some gas in here like this. And maybe this side is, let's go pink. We got, this one is pink. They're both helium though. So they're actually both the same gas. It doesn't really matter which gas it is. Okay, how are you gonna find pressure? So initially, this is 2 atmospheres and 9 liters. So you have pressure and volume, PV. Does that sound familiar? Which gas law are we talking about? And over here, this is 3 atmospheres and 3 liters. The problem is when you open this, what's gonna happen? That's right, it's all gonna mix, okay? It's all gonna act like it's the only person in the room, and the pink is gonna flood out and fill the whole space, and the green is gonna flood out and fill the whole space. And so it's gonna be a totally new pressure because they're mixing, and it's gonna be that equalizing pressure. You can figure out volume though. This side's 9 liters, this side's 3 liters. So guys, what's the total volume? Yeah, total volume is 12. All right, I give you a lot of hints just then. I want you to pause and I want you to try it. It is a monster. At least think through how would I solve it? There is more than one way to get this answer. And try plugging in some values and see what you get. So pause now, try to solve. I'll come back and help you out. Okay, this is a little interesting to solve. What I'm gonna do, guys, is I'm gonna solve them individually. I'm gonna do a Dalton's law. Dalton's law says they act like they're the only person in the room. So I'm gonna solve this one, and then I'm gonna solve this one for their new pressure. Because this is 2 atmospheres, right? As soon as I open this, it's gonna flood over here, and that pressure actually will drop. The green's pressure will drop. Same with this one, it's 3 atmospheres. As soon as I open this, it's gonna flood out, and that 3 atmospheres will drop for the pink. So I'm gonna get the new pressure for both, and then I'm gonna add them together, okay? Okay, let's solve this side. We got pressure and volume, PV. Which law is that? That is Boyle's law. Boys play video games. So P1V1 is equal to P2V2. My initial is right here. Pressure is 2, volume is 9. I do not know what the new pressure is. That is what I'm solving for. Do I know the new volume? Yeah, volume, I mean, this is 9 liters, this is 3. It's like a hard glass container, okay? So you add them up, you're gonna get the new volume. That would be 12 liters. Solve for P. You get pressure is equal to 1.5 liters. We're gonna do the same thing over here. So this is the new pressure. Once this opens and the green one moves over, that's its new pressure. Let's do the same here, okay? P1V1 is equal to P2V2. Initial pressure volume is 3. Volume is also 3. We're solving for the new pressure once it opens. We know the volume is 12 liters. Solve for your pressure. You might actually be able to do that one in your head. That is 0.75 ATM. Now, this is the pressure of the green one when it opens. This is the pressure of the pink one when it opens. What's the total pressure? Ah, you see, this is where we use Dalton's law. So we're gonna come in here with Dalton's law to finish this out. P total is equal to this one plus this one. So it'll be the 1.5 liters plus the 0.7, sorry. I messed up, didn't I? That's not liters. Pressure is atmospheres. 1.50 ATM plus 0.75 ATM. You add that up, you get 2.25 ATM. So there is a different way to solve this. You can actually set this up mathematically like an algebra equation and solve it that way. Perhaps some of you did that. If you got that number, way to go. That's definitely a bit of a monster to solve. But now we have slain the monster. All right, that is it for today, guys. Have a good one. I'll see you later.